there, we find the reflected one goes off in that direction. Yes. Well, it's just the lines will cross, but you don't have to. Okay. Yeah. Angle of incidence, angle of refraction, and they are the same. All right. And then the refraction of a water wave, we said it is the wave will change direction when it travels from one medium to another. The reason for the direction change, it travels either faster or slower in the different mediums. In terms of water, we said the shallow water represents the part where it goes slower, and it goes slower because the wavelength becomes shorter. Okay. The wave changes direction in such a way that we say the direction of the wave changes, it bends towards the normal when it goes from deep water to shallow water. Interesting, or what you need to remember, this dotted line is the normal. So the angle of incidence lies between the ray and the normal. And over here, the angle of refraction also lies between the ray and the normal. All right. Then the diffraction, here's just another picture of waves in a ripple tank. And very clearly, you can see there is the wavelength of the wave. All right. And over here, if you went and measured it, you will see that the wavelength has become shorter. And then very clearly, the direction has also changed. The normal would lie over there somewhere. All right. Angle of incidence would be there. Angle of refraction would be there. Okay, now diffraction then of water waves, we said that it is the bending of a wave when it travels around the edges of an obstacle or when it travels through a tiny opening. There were two factors that influenced the amount of diffraction. Can you remember? It is directly proportional to the size of the opening and inversely proportional to the wavelength. No? Just the other way around. Just the other way around. It is wavelength over that. There. There. Are you with me? All right, people. Here we just have a picture of water waves taken from the top. You can very clearly see. Oh, seriously, why is this moving around? Just let me lock it in place. Right up there. Come on. Okay. Very clearly, we can see the water waves have been bent. Okay. Around over here, you can see there's even more bending around the edges of the obstacle. All right. Some more diffraction, size of the opening. If you have a big opening, there's less diffraction. If you have a small opening, there's more diffraction. The optimal amount of diffraction would be when the size of the opening is similar to the wavelength. All right. We had a look at some of the videos. Now we have some more videos, but I first want to explain interference. Now, interference is higher level only, okay? The questions, page 315. Oh, that's not in your... No, it is. It is page 315. You can have a look at them, 18.1, 18.2, 18.3, 18.4, 5, and 6. 3 and 4 is for higher level only. So you can mark them. The ordinary levels, you can start with that. I want to do interference with the higher levels. Okay. We'll only do the homework. 6. So it's 1 to 6, but only 1B. And then 2, 3, 4, 5, 6. All right. So, with interference, we've already said that, or I've already said when we've started with this, if I have a torch with a beam of light, and I have a friend also with a torch with a beam of light, and we crossed our beams of light, the one beam can go through the other beam. And there where they go through it will be slightly brighter, and afterwards they will each continue on their own way. All right. Now, here we're going to have a look at what exactly happens. So, I have water waves, and it's approaching, well, a barrier, and we have 2 openings. So, each wave is going to be diffracted. Are you with me? All right. Now, in this diagram, I have 2 openings. So I'm drawing the diffracted wave of the one opening in green, and I'm going to do the diffracted wave of the other opening. I'm just doing it in red. Okay, now I basically have water waves that somewhere along the line they are going to cross each other. Well, oh, come on, back here. They are going to, for example, okay, I can draw it like that. Cross each other like that. Or at the other extreme, this is what is going to happen. The one wave is going to become superimposed on the other wave. Okay? It is going to result in a new wave, and the shape of that new wave is going to depend on whether I'm going to add the amplitudes or I'm going to subtract the amplitudes. Can you see over here? That amplitude and that amplitude is going to cancel, and I'll get no movement. So a wave plus another wave can give me no wave. Okay? We call this destructive interference. But in the same sense as one wave can cancel another wave, they can add together. All right? And it can result in a new wave. Well, there is the red amplitude and there is the green amplitude, and I will get a new resulting wave. We call this constructive interference. Well, there are grades in between. All right, we look at the extremes. Okay, so what is going to happen in this diagram, and I'm going to remove my color because my whole thing shifted. Oh, maybe I can get it back. Okay, more or less. Now, the red wave, the line that I've drawn over here represents the crest of the wave. The center of this hollow is going to represent the trough of the wave. All right? So, where my green line and my red line cross, there, at that point, let's do it in blue, that point, that point, that point, there, there. What is going to happen in terms of which one do we have? Yes, I have constructive interference. Can you see that? All right. But, and now I need to use, okay, I'll take the black one. Can you see over here? What do I have? The red part is the crest, and it's in the it's in a trough part. So where the crest and the trough land up together, we get destructive interference. So what is going to happen is we will get bands of constructive interference, okay? And in between, we are going to get bands of destructive interference. It's going to result in terms of water waves. Have a look at this. Here's our two sources, okay? Our circular wave fronts there, okay? And now they start interfering with each other there. Can you see we get areas where there are waves, and we get areas where there aren't waves? What has happened over here? Constructive interference. We've got bigger waves. And what has happened over there? Yes, that is destructive interference. No waves. Okay. So, if you went and looked over here, you stood over here, here we would have constructive interference, there we would have destructive interference. There's constructive. So we will get bands of constructive, destructive, constructive, destructive. In terms of water waves, we can see the picture. What does this mean in terms of light? So what would constructive interference of light imply? Brighter. Destructive? Or no light. So light plus light can give me darkness. Okay? Okay? In terms of band of light, band of darkness, band of light, band of darkness. I'll show you. In terms of sound, what does it mean? Sound? No sound. Sound? No sound. Do you understand? What happens in a theater where we have opera, etc.? They've been built to a specific shape. Why? For the acoustics. Because there's going to be reflected sound, there's going to be some interference. There's one extra thing that we need to know, why my sound wave doesn't interfere with his sound wave. There's a reason for it, okay? But are you with me, what I'm trying to explain to you? Okay, now, for interference to occur, we find that the waves, these two sets of waves, my red set and my green set, must have the same frequency. If they don't have the same frequency, they won't interfere. They will superimpose and they will move through each other, but they won't cause interference as we have over here. All right? All right, so for interference, we need the same frequency, light, sound, wave, whatever. All right. Okay, I think I must stop the video at this point, and then I want to go and have a look at some of the videos that we can see if you can see something there. Okay.